The final topic we're going to be discussing in Chapter 28 on kinetics is how does temperature affect kinetics. So temperature is one of the main drivers behind how fast a reaction will go. The other one being concentration, which we've already addressed in talking about rate laws. So this is a figure from your textbook that shows sort of different ways that you can have a temperature dependence for a reaction. The most common is what's shown in A, and what we're mostly going to be talking about in this chapter, which is a temperature dependence that shows an exponential behavior. So the rate increases exponentially as the temperature increases. And so this is described by the Arrhenius equation, which we're going to be going over in just a little bit. So we would call this Arrhenius behavior. The second type in plot B is a reaction that has Arrhenius behavior at lower temperature, and then you reach a certain critical temperature and the reaction runs away. So basically the rate becomes infinite. So it reaches some critical temperature after which there's sufficient energy in the reaction that it just sort of explosively goes. So this would describe something like an explosion or a chain reaction, where once you reach that critical point, the reaction proceeds very quickly, and you know that's something a little bit different than just strictly Arrhenius behavior. The third example is a reaction where maybe it's where increasing the temperature actually does something to one of the reactants, either decomposes it, or I think the specific example here is this would be like an enzyme catalyzed reaction, where as you increase the temperature at a certain point, the enzyme no longer functions properly, and so the rate of the reaction plummets once you reach that point at which the enzyme denatures or whatever else is happening to the protein, and so you get a massive decrease in the rate instead of an increase in the rate as the temperature goes up. But again, we're going to be focusing mostly on A here, but just be aware that this is this is not the only possibility of this exponential increase in reaction rate. So this sort of behavior is there's an empirical equation, so based on experimental data, that this Arrhenius behavior is governed by this equation, where we have d log little k. So this is not to be confused with the equilibrium constant. This is the rate constant, since we're talking about kinetics. So the rate of change of the natural log, and that's not time, that should be temperature. The differential of the natural log of the rate constant with respect to temperature is given by this empirical formula, a constant that's called the activation energy, divided by RT squared. Okay, so we can integrate this to get an integrated form of this equation. If we integrate this, we'll get log k is equal to natural log of some constant that we call A minus EA over RT. Or we can say that if we take the exponential of both sides, we get k times e to the minus EA over RT. All right, and this is what's known as the Arrhenius equation. So in this equation, again, EA is the activation energy, which we'll discuss a little bit more in a few minutes, and A is called the pre-exponential factor because it comes before the exponential. Very very clever name, I know. And what this factor has to do with is basically what fraction of molecules when they collide are in the right orientation relative to each other for a reaction to occur, or have sufficient energy or things like that. So as the temperature, so this is something that sort of doesn't depend on the temperature, the pre-exponential factor. But as the temperature increases, you get more and more molecules that have sufficient energy to overcome this activation energy barrier that we'll be talking about a little bit. Now, one assumption here, one big assumption here is that in this integration that we've done, is that the activation energy doesn't depend on temperature. So if there is a temperature dependence here, then this equation would be more complicated, and you would need to know how EA changes with temperature. Okay, so if we want to understand the temperature dependence of a rate constant, what we do is we need to measure K, measure rates. This is something that you have done or will do in lab, but measure what's the rate constant as a function of temperature, right? How does the rate change with temperature, and measuring that. And then we can plot the natural log of k versus 1 over t. Because if we go back up to this equation above, we can see that this has the form of a line. Y is our natural log of k. M, our slope, is equal to EA over R, negative. And our x is 1 over t. And then this is our intercept here, is the natural log of this pre-exponential factor. And so if we plot natural log of the rate constant versus 1 over temperature, we'll get a straight line. And the slope of that line will be equal to activation energy, negative of the activation energy divided by R. And so this is how you can determine activation energies for reactions. It also lets you determine the pre-exponential factor A, because you can get the intercept, and then that intercept is equal to the natural log of A. And so this is experimentally how you would do this. The other way you can use this equation is if you integrate it between specific limits, similar to what we have done with other equations similar to this in this class. Is we can write this as a natural log of between two specific limits, right? K at t1 divided by k at t2, right? So this is not k multiplied by t1, this is but saying at that specific temperature, is equal to EA over R times 1 over t2 minus 1 over t1, right? This is looking at specific limits on the integral instead of indefinite integral. So the pre-exponential factor doesn't show up because you're doing a definite integral. And using this, we can go ahead and calculate specific values for specific temperatures. So we'll pause the video here. We'll go through an example of doing that in the next video, and then also talk a little bit more about what activation energy means.